In this sequence, we will look at a major application area of the frequency method of analysis, okay, and also of the impedance method. This major application area is called filters. Filters have some frequency response, and as signals go through these circuits, those signals are transformed according to their frequency components. Now, in the past, in the first many weeks of this course, you looked at time domain analysis. Okay, so we had some Vi of t, and the circuit processed that input signal, and you looked at time domain behavior. Now here with filters, we look at the frequency response of circuits and how they process signals coming through according to the frequencies contained in those signals. So just to put this kind of analysis into perspective, let's go back to what we've seen in the rest of this course. So let's do a quick review of where we are and how frequency analysis fits in with the grand scheme of things. So we started off life by saying, let's work with lumped circuit abstractions, and we had a playground here. This was a ECS playground. In this playground, good things happened, and the lumped circuit abstraction applied. We made some of the assumptions that enabled Maxwell's equations to simplify into much simpler algebraic analysis through the lumped matter discipline. Now, once we got into the ECS playground, we looked at two classes of circuits, linear and nonlinear. Methods like the node method and so on applied to either linear or nonlinear circuits. And then we looked at a bunch of special methods like superposition, Thevenin, and so on that applied to linear circuits alone. We then looked at digital circuits, and it turns out that although the behavior of digital circuits is nonlinear overall, once you fix all the switch positions, okay, digital circuits are composed of many switches and other components. If you fix all the switch settings, you are left with generally a linear subcircuit, at least according to the SR model of the MOSFET that we learned about. Going back to the analog domain, we looked at the small signal method. Okay, we looked at circuits that were nonlinear, but then we said that if we biased the circuit to some region of interest and focused on very small signals, then the response of those nonlinear circuits was more or less linear. This gave rise to the small signal method. A lot of devices are nonlinear, and by focusing on the small signal method, we got very useful behavior out of those nonlinear elements as well. Okay, most recently we looked at sinusoidal inputs. We said that you can take repetitive signals and you can show that they're composed of many sinusoids, and so we said if we could understand how circuits behave to sinusoids, we can study all the other repetitive signals as well using this whole Fourier series method that you will learn about in other courses. So we looked at sinusoidal input, and then within that category we said let's focus on the steady state. Okay, let's look at how the circuit behaved after a long period of time so that the transients would settle out. In this case, our analysis was dramatically simplified, and we introduced the impedance method. With this method, we could take our circuits and replace each of the elements, such as resistors, capacitors, and so on, with their impedance models. And the impedance models showed how they behaved with respect to frequency. And we further showed that when we did that, the analysis became almost similar to the resistive analysis for circuits containing resistors. And all we had to do was build resistive dividers and adders and resistive dividers and various other components, series parallel simplifications of resistors and so on. And impedance behaved very much like resistors. So that was the beauty of the whole sinusoidal steady state. Let's continue with our review, and let's do a quick example of how the impedance method applied. So let's say, for instance, I have a little circuit with an input Vi and some resistance R, capacitance C. Suppose my Vi was some sinusoid given by something like Vi cosine omega t. And let us say I was interested in the signal across the capacitor. I could apply sinusoidal steady state analysis, and using that I could find the steady state response to this input sinusoid. To do so, what I said we have to do is replace each of our components with their impedance models. Okay, so for example, I replace my voltage source with a voltage source which I decorate with the amplitude, okay, the real amplitude of the cosine. Okay, the amplitude of the cosine input. If I have a complex signal, then I simply stick the complex amplitude of that complex signal. I replace each of my components with their impedances. Okay, so the resistance would be replaced with its impedance model ZR, and the capacitance would be replaced with its impedance model ZC. The signal across the capacitance would be capital V, small c. Okay, notice the notation here. Capital symbols with small subscripts imply complex amplitudes. Okay, so now my signals here are complex amplitudes and my impedances are ZR and ZC. Recall, ZR is simply R and ZC is 1 by SC, which is the same as 1 by J omega C. For inductors, ZL is J omega L. So now I can use the impedance method and very quickly do a resistive divider action to find VC as a function of VI. So VC is simply equal to the impedance across which I'm measuring VC, divided by the sum of the impedances ZR and ZC. I can figure out the transfer function, VC divided by VI. Okay, so this is the transfer function. Okay, and what I can do is, and I get that by taking VC over VI. So continuing with the analysis, I'm now going to replace my impedances with the actual component values. So I get 1 divided by J omega C for ZC. I get 1 divided by J omega C for ZC again, and I get R for the impedance of the resistor. If I multiply both the numerator and denominator with J omega C, what do I get? I get 1 in the numerator, and I get 1 plus J omega RC out here. Okay, so the transfer function VC over VI is simply 1 divided by 1 plus J omega RC. So notice how easily I derived this expression that showed me that I can get the complex amplitude of the voltage across the capacitor simply by multiplying the real input amplitude VI by 1 divided by 1 plus J omega RC. So I would be left with some complex value for VC. And then you know all the good stuff. You know how to get the real value of VC from the complex amplitude VC according to this expression. So VC cosine omega t plus phi, where phi is the angle of VC. Okay, so this was pretty straightforward, and you've seen this before. So what this says is that once I figure out the complex amplitude VC, then I know everything. Okay, I can very quickly figure out the exact voltage, the time voltage across the capacitor according to the magnitude of VC times cosine omega t plus phi, the phase of VC.